Okay, everyone, welcome back. So I posted the exam 1 grades yesterday. If you have questions about what you got wrong, the Scantron and the testing center did not mark which ones you got wrong, but it does give me a data file that tells me which ones you got wrong. So if you have any questions, let me know. Come see me in office hours and I can help you out there. And I can give you your exam back. So let me know. Otherwise, after everyone's taken the exam, still waiting on one student to take the exam. I'll calculate the curve, put that in there, and then that'll be your final grade for exam 1. So we'll do that for each of the exams, but I need all of the exams in before I can put the curve in, if that makes sense. So we'll do that for each of those. Please don't forget about exam 2. It'll be in person. I'm not using the Scantrons because I think it's too much trouble than what it's worth. I'm just going to grade them by hand just so I can get it done over the weekend and get it back to you quickly. How's that sound? Does that sound good? I figured. So that's what I'll do. There's not too many of you in the class, so it's not going to take me long to grade. That was just a recommendation from past professors that recommended I do a Scantron. So we'll just grade it by hand. That'll be easy. So we're going to pick up where we left. You're talking about longshore current and drift. Remember, drift is the sediment that is moved by the current. The current is the force that is enacting the movement. That longshore current is the general direction that the sediment is going to move, but it's the wave action that's going to help move that sediment. So it comes in at an oblique angle because the wave wants to go in perpendicular to the shore, but because of the longshore current, it comes at an angle, washes up onto the shore, digs out some sand, takes it back perpendicular, and then it continues that zigzag movement all the way down the shoreline. So that's going to end up giving us some interesting geomorphic features that we talked about, like spits, barrier islands. So based on where the sediment is accumulating, we'll be able to tell the direction of the longshore current. The sediment accumulates in proportion to the directional component of the longshore current. So as sediment is being moved upwards in this image, it's being pushed around and elongating the corner of this spit. So that's going to continue to do that over geologic time and on really short time scales. So we can see this happening over like a year in our life. So they're pretty cool features and we can map them out. We talked about barrier islands. Okay, so we're going to start talking about the littoral zone. It's littoral, not literal. The littoral zone is the area where we're having all of this, we're having erosive actions from waves. We're also having deposition from smaller waves. So it's really where all these things interact and create a unique beach front and a beach surface. So we have the swash zone where we have the shallow water. It's the kind that you can wade in, maybe up to your knees, where all of that sand washes in and out. So it's going back and forth, changing constantly. And we have the surf zone, the deeper portions. Just imagine you can surf out there. You're not going to be able to touch the bottom, where we have those larger breakers, not the real gentle stuff that we have up closer to the shoreline. So it's the power behind all the wave action is what's going to erode the beach face, as well as whenever we have those lower energy waves, that's going to deposit stuff onto the beach face. So the beach face is going to go over all these different periods of erosion and deposition in a natural system. And we'll talk about how we impact the beach surface today. So let's talk about the berm. The berm is that flat, sandy area where everybody puts their umbrellas on the beach, way far back from the shoreline where all the water is actually swashing and moving around. Back further, probably where the boardwalk is, as you can imagine, you're going to have the beach cliff or the cliff face or dune line. That's where you have all of this stuff just falling due to gravity onto the berm, and that's where all our sand is going to deposit. So eventually, due to wind, that's going to travel down the beach face and into the ocean, where it's going to interact with the water, and we're going to get these different changes in the sediment. So the way we look at these changes in sediment is we do a sediment budget. Much like you would do a budget for your own personal finances, we can do this in a real simple equation for sediment systems. So basically, it's all based on inputs and outputs. Just like when we had discharge for rivers, we're going to do the same thing with the sediment that is in those rivers and water systems. So input, we're going to denote as positive. Output, we're going to denote as negative. Makes sense, right? Input, you're putting stuff in, you're adding. Output, you're taking stuff out, you're subtracting. So we have all these different transport systems like the river, the ocean, and then we have these storage reservoirs for sediment. So like the sandy beach, that's going to be our biggest portion of storage for sand. That's where all the sand is going to be stored. So we have growth on the beach whenever we have a greater input than output, and we have erosion on the beach whenever we have less input than output. Just part of that equation. If you have, at the end of the day, if you have a negative part of that equation, you're getting output. Positive, you're getting input. You're growing the beach. So if we look closely at this diagram, we have in our legend, we have longshore transport, sea cliff erosion, submarine canyons, and rivers. And that's going to be denoting the sediment transport for each of those systems. So let's start with longshore transport for SL, longshore drift. This is an input. It's a positive change in the sediment system. So we're adding sediment to this specific portion of the beach. All that sediment from upshore, the longshore is coming down to the south. It's going to carry all that sediment along the shore with it, and we're going to add sediment into this beach system here. So this is all based on wind and wave intensity. So as you can imagine, more waves, more energy waves, more erosion, updrift, more deposition in this system eventually. So that's longshore drift. And obviously we can tell the direction based on where all the deposition is. We have deposition on this side. That means the current has to be coming from the north. Okay, sea cliff erosion. That's where we have our dunes. So eventually, if we get big storm surges, we're going to get some wave action that's going to chomp away at those, take some of that sand down onto the beach. We can have landslides if it's not a really stable cliffside. That'll just bring stuff down onto the beach as well. So just simply gravity. And eventually, if we have any like maybe runoff during a storm, that can carry some of that down from the cliffside down onto the beach. So that's also going to be an input. We're adding sediment from different types of erosion, not wave action. Okay, so what's a sea cliff? We talked about these a little bit. We have sea stacks and sea cliffs. These are rock surfaces. These are erosive and active parts of the coastline. So the ocean is gonna, this is a claymation, not a terrible claymation of it, but eventually we're gonna cut a hole in that from the wave action. Remember, it's those vectors of the waves kind of hug that headland. So it erodes around it and it leaves that stack there. And eventually it'll keep doing the same thing until that stack is removed, makes the stack smaller, they'll just fall over each other. So that's what sea cliffs are. We talked about that when we were talking about wave directions. All right, so obviously rivers eventually run into the ocean too. So rivers, remember, carry all of that sediment in suspension, sometimes in the bed load where it just rolls along the river bottom. So we're going to get an input of sediment from river systems. So that's a positive sediment budget. So we're eroding stuff from way up in the headlands, up from the mountains, carrying it all the way down the rivers. It's coming from that direction, obviously, and eventually it'll go out into the sea. Most of it will get deposited around the beach closest to the river, obviously. Some of that will continue to move because it'll get caught in the longshore drift. So we're interacting our different sediment sources. So we'll eventually get to developing deltas like we have in most other river systems. Like think of the Nile River Delta. It has that weird fan-like shape at the mouth of the river. That's all that sediment coming out of the river, depositing in these low energy environments. And eventually they'll start to shift and create new shapes because of the longshore drift. Okay, so let's say we're looking at SR. That's our sediment from the river. And let's say we build a dam right at the mouth of that river. What effect is it going to have on that sediment coming from the river? Increase, decrease, or no change in the sediment? Adam. Decrease. Why? Dam will block the sediment. Anybody disagree? Anybody agree? Yeah, that's right. So we're going to have a decrease in the sediment. Obviously, the dam is going to trap sediment. This is a big problem with dam building and something that they have to keep an eye on, because if there's so much sediment built up on one side of the dam, it creates an unstable load and weight on one side of the dam. So they have to monitor sediment and calculate sediment that would be trapped in that watershed before it reaches the dam, and figure out a way to either dredge or mitigate. Maybe some of that stuff is useful. If you have like real good quality clay coming out of suspension, you can use that for like making bricks, stuff like that. So some of it can be, you have an economic advantage. Okay, so all of those that we were talking about were inputs. Now we're going to talk about outputs. And really, that's just from sea canyons that we have, those submarine canyons that are underneath the surface of the water. So we get all that stuff transported from longshore drift, from the rivers coming in. All that is deposited on the beach surface. Eventually, we're going to move out of the beach cell with all of this coastal erosion. So we have all this, these longshore currents. Remember, it's not just the movement of it, it's the wave action coming up and taking it away. Some of that moves, some of that gets taken out all the way into the ocean. We're taking all that sediment out of the sediment system. So that's a negative in our budget. So obviously, if you have sediment that's fine-grained enough, that's light enough, you can just carry it away by wind. So there's this whole mapping project that maps out what's known, it's called LOESS, L-O-E-S-S. It's this sediment that's light enough that it carries wind. So there are actually deposits in like the central part of North America that we can trace back to their original place in the Sahara. So wind, just all this wind is transported across the Atlantic Ocean and deposited in North America. Just crazy to think about. So that's a way to do it. Obviously, wave action is going to pull that out. And then gravity, of course. Remember, just because we're at the shoreline doesn't mean that gravity doesn't take effect here. Once it's under the water, it's going to keep falling and falling because we're on a continual slope. Remember, the shelf is a gradual, steady slope. And eventually we find these submarine canyons. Remember, the mouths of these rivers at lower sea levels used to incise deeper into the continental shelf. So we get these large underwater canyons that are still carrying sediment, and they're going to take it out of the beach system eventually. Those will eventually get deposited on the sea floor, where they're going to stay there for probably millions and millions of years until they turn into rock. Just because there's no energy going on at the seafloor, there's no wave action, nothing's, the only thing stirring it up is like marine life, some bottom feeders, stuff like that. So all those sediments, once they're taken down into the submarine canyons, they're not going to enter back into up back into the beach cell, into the littoral cell. So we're not gonna get any more action from that. So if we calculate all of this together, we're gonna get a sediment budget, and we're gonna see this littoral cell in play, and we can see if we have positive sediment budget where we're gonna have beach growth, or we have a negative sediment budget where we have more erosion. So we're gonna shrink that beach surface as a whole. Okay. So do your best with this picture. So we have, this is Charleston Harbor in South Carolina. We have A right here, B and C. These are going to be areas of the littoral cell. So which one of these letters best represents where a submarine canyon would be? Yeah. C. C. Very good. It is going to be C. So we were a lot further off of the current shoreline. We're away from most of the sand deposits. That's where we're going to take stuff away from the beach surface. That's where our erosive component is going to be. How about sediment input from a river? Which one of these? A, B, or C? A. Very good. Yeah, we're at the mouth of the river. That's where the most sediment is going to be coming from. So obviously we're going to get an input of sediment right at the mouth of the river. Very good. And finally, kind of limits your choices. Which one represents sediment input from longshore drift? Everyone. B. Of course it's B. So this is where we get, we're depositing some stuff on the shoreline, but most of the movement and transport is going to be happening just offshore in that wave action, that swash zone. So right there at B. Okay. So that's how sediment moves on coastlines. And as you can imagine, we have some problems with that. If we start moving sediment away from coastlines and we start decreasing the beach surface, are people going to want to live there? Probably not. Most people like living on coastlines because they like going to the beach. They like the picturesque value. Obviously, tourism is a plus too for the local economies too. So if you have an erosive beach, you're going to decrease your economic value of the beach overall. Can also create instability in the barrier island system. So there's a lot of money that's shifted into mitigating coastal erosion and beach erosion. So this isn't just on the federal level, but mostly state and local governments are heavily invested into mitigation strategies for maintaining beaches. So for example, this is Fenwick Island, right around Ocean City. This is a hugely developed. As you can imagine, if there was nobody living on Fenwick Island, you'd probably have erosion, you'd have deposition, you'd have this really dynamic island that moves over time. Now that people live there, people tend to like it when their houses don't move geographic locations after you've built it. So what do you do to mitigate against that? So this is Cape May, New Jersey. Those lines are past shorelines. So obviously, as we start building stuff on the coastline, not just for tourism value, but that's where our harbors are for shipping. Anything you order online that comes from another country has to be shipped here on a boat. So we need harbors that are going to be stable enough for deep keel boats and shipping. So we're going to end up spending a lot of money. But as you can see from this image, we have a lot of erosion over time. That purple line at the bottom, that was measured in 1879. So the reason we know these so accurately is because obviously we had maps in 1879. We're able to import those maps and digitize them and see where past surfaces were. I used a similar process when I was working in Slaughter Beach in Delaware Bay. There's a map from 1852 that I was able to put on this marsh surface, and I found that there used to be a natural river running right through it. and it matched almost exactly where we're finding all these really weird geomorphic features on top of it. So that was a really cool thing to do. Go to the DGS, find this super old map from 1850 and digitize it, which is a pretty cool thing to do. But obviously with continued development, because you're not going to stop developing, but you have to stop this erosion somehow. So how are we going to do this? So we have a couple of case studies that we can look at. So Ocean City is a really good example. A lot of you have probably been to Ocean City. It's not too far from here. So we have all these barrier islands off the coast of Maryland. We have Fenwick Island up to the north. Ocean City is right at that inlet at the south part of Fenwick Island. Fenwick Island ends in the red. We have Assateague Island, which is a state park. And then we have getting down further and further, we're getting into like the Virginia beaches. So this is a hugely developed area. Very large population. A lot of foot traffic in summer months, as you can imagine. It's the only coastal place in Maryland for like coastal resorts. We get 8 million people a year visiting just these real tiny islands off the coast of Maryland, which is a crazy amount of foot traffic. However, that's in Fenwick Island and near Ocean City. Assateague Island is a state park, so obviously there's no development there. It's protected by state law, so we have less development there. So this is that green that you see there. That's the historic shoreline. So we're looking at historic shorelines from maps, then from aerial imagery, and then after that, we're getting satellite imagery and what we see today. So most of what you see in gray from 1962 on, that's pretty stable. It hasn't really changed much since then. But as you can see, so we have Fenwick Island up to the north here, north of where it says inlet. We have Assateague Island to the south. So as you can see, Assateague Island used to be a lot further east. Slowly but surely, it's moving further and further inland. So this is where we get this, what's known as transgression, where the barrier island is moving slowly towards the shoreline. So transgression, the barrier island is moving towards the shoreline. So this is how we describe barrier islands, mainly the direction they're moving. Transgression is when they're moving landward, so we're moving closer to the shoreline, or eventually we're going to become part of the shoreline as the barrier island. And regression is where we're moving seaward. So we have more sediment supply, we're building up the barrier island itself, so we're able to move and widen that, that barrier island further and further out into the sea. Remember, barrier islands are built by sediment. So if you have a bigger sediment supply, you have a positive sediment input, you're going to build out more and more. But if the sea level is rising faster, you're going to erode more and more than what you can replace in it. So we're going to move further and further back away towards the shoreline. So transgression, moving landward; regression, moving seaward. Keep that in mind. Okay, so Ocean City, they allow building on dunes and in front of dunes, which becomes a problem because, as you can imagine, dunes they may not look like much, they're just hills made of sand, but they're a super important feature in the land surface. So in a natural system, in the winter, this is where you have more of your high water systems. So you're going to get some erosion, right? That dotted line is where the berm used to be. So all the high water that we get in the winter, we're going to erode away that dune. But during the summer months, that dune is going to eventually fall over, replace the berm, and eventually from wind, from wave action, it's going to build the dune back up. So in this natural system, even though it's going to be moving around, the dune helps to replenish the berms. It helps to provide this equilibrium of deposition and erosion. So why do we want to mitigate? Obviously, the beach is a really valuable commodity. We mentioned the economic value. And the best thing that we can do is engineering structures, because we're going to continue to develop on coastlines. We're not going to move people out of Ocean City, obviously, but we have to find a way to prevent that that island that it's on from disappearing. So we have a number of ways of doing that. So we're going to talk about hard structures first, like hard engineering, actual like building of things. So these are what's known as jetties. Jetties are just two parallel structures made of, can be steel. Most of them are made with broken down rock and wood, and it's like kind of wrapped in this chain link fencing. So you build these huge structures that are dug into the sand at the bottom of the shoreline there, right at the mouth of the river. So as the river is flowing, it gives it a little more time to gives it a little bit extra channel to take that sediment out, and all of that longshore drift is going to end up depositing on that left side there of the jetty. So remember, based on where the deposition of the sediment is, that's where we know the longshore current is coming from. So since we have deposition on the left here, the longshore current has to be coming from the left. It has to be bringing sediment in from that side. So jetties help to break up the longshore current. You get more deposition on the leeward side, and you get a little bit of erosion on the starboard side, away from the longshore current. So this is going to interrupt that longshore drift system. Yeah, so remember, this is the direction that we're moving with longshore drift. The wave wants to go this way, perpendicular to the shore. The longshore current is going parallel to the shoreline. The wave is going to move along with the longshore current at an oblique angle. It's going to tear stuff away, but it's going to deposit along that jetty, because the jetty is blocking it. So this creates changes in where deposition occurs and where erosion occurs. So if you have an area where you want to create a little bit more deposition, and an area where you can allow a little bit more erosion, these are great for that. So this is the jetty right at the mouth of Indian River Inlet. That's in Delaware. So we have the river system is coming out towards us. We're looking at it from the ocean right here. That jetty is blocking on either side of the river channel, allowing that. We also have that bridge going over the top of it. So based on, if we're looking at it straight on, where's the longshore current coming from? Remember, where the sediment is deposited, that's where the longshore current is coming from. So where do you think? Is it A, coming from this direction, B, going in that direction, C and D going up and down through the channel? Yeah.
I would say
A. What's making you make that choice?
the bulk go up.
The bulk buildup. Exactly, very good. So it is A. So if you notice this shoreline on this jetty, it's a lot further back. That's where the erosion is. But we have a lot more deposition on this part of the jetty. Remember, that jetty goes all the way back to, you see where that channel kind of narrows into a bottleneck? That's the start of the jetty. So we have a longer jetty on this side. We have that buildup of sediment over here. So that's where the longshore current is coming from. It's going in this direction. All that sediment is coming from over here, hitting that jetty and getting deposited. Because of that, we're getting erosion on the other side. Okay, so now we have an Ocean City jetty. After we had a really bad hurricane season in the 30s, it basically went over top of Assateague Island, Fenwick Island. There was really no way of preventing it, of course, because it's a hurricane, but it really eroded a lot of the sediment away. As you can imagine, having water just smash over an island is going to take away all that sediment. So what they did was they built a jetty right at the mouth of the river coming out in between Fenwick Island and Assateague Island. So it allowed not only for ships and boats to come up that river, smaller boats, shallow drafts, but it also enabled a lot of ocean life to swim up into the bay. So you get a lot of marlins in that area as well. So it's pretty good for fishing. And this is what that looks like today. So as you can see, Assateague Island has been moving landward. So that's transgression, moving landward. But ever since this jetty was installed, it has not moved at all. So it's been pretty stable ever since that jetty was put in place. So before that, they had a lot more development on Fenwick Island. We had a lot more deposition over here, but we're still going to get some increased erosion because we're widening the beach where all the tourists are. We're going to increase that beachfront so we have lots of room for lots of people to visit. We're decreasing the sediment load over on Assateague Island, but it's not moving landward anymore. So we're going to be able to keep this back channel in the back bay open. Okay. So now which direction is this longshore current? Yeah. B. What makes you say that?
Just because you can see
That's exactly right. So we get more deposition from where the longshore current is coming from. So always keep that in mind. So you guys should be pretty good at that. So I said this, let's see if you're listening. Is Assateague Island experiencing transgression or regression? Yes. Regression?
Yes.
No. It's transgression. So put it in simpler terms. Transgression, we're moving towards the land. Regression, we're moving away from the land. I know it sounds like counterintuitive because I always got those mixed up whenever I was in undergrad, but transgression, we're basically changing the island into part of the shoreline. Regression, we're going to take it away from the shoreline. Okay. So these are other hard structures that we can build. Once again, thank you, French people, for coming up with the word groin. So these are just built at right angles. They're perpendicular to the shore face, and you can have these at regular intervals. So rather than getting at the jetty where you have deposition on one island and erosion of the other island, if you put these along an entire beachfront, you'll get erosion in some places, deposition in others, and that it's going to create a bit more equilibrium. So you're going to create a more stable island surface, more stable barrier island. So just by having these structures, obviously creating a barrier to the longshore current is going to slow stuff down. So obviously we're going to have deposition on the updrift side, erosion on the downdrift side. So the easiest way to think about this, if you think of those pieces of sediment as like arrows, they're pointing in the direction where the longshore drift is coming from. It's not pointing down the longshore drift, but it's pointing at the source. So longshore drift, in this case, is going this way. Get deposition on the drift side, erosion on the back end of the groin. You can also have breakwaters. So these are really important just because they can create protection for mooring. So if you want to create a harbor or somewhere on the beachfront because you have some deeper a deeper basin right there, you can create this breakwater, which is all these are made of the same materials. You break down some big chunks of boulders of rock, you wrap them together in some type of chain link fence, and you just plop it down wherever you want it. So the material cost is pretty low. The engineering cost is pretty low just because they're pretty easy to install. It can't be that hard to dig a hole with an excavator and then throw stuff in it. So they're connected to the shoreline, and they're gonna create another slowdown of longshore drift. So all that deposition gets deposited all right in front of the breakwater, so that it'll help you grow your breakwater. So you could maybe plant vegetation on there, make it more stable, make it more of a permanent surface. And as you can see, we're getting almost a spit on the edge of that breakwater. So if we allow that to continue, it may end up closing off that breakwater bay. But instead, if we can take some sediment away from it, dredging it, will keep that breakwater open. This is what that looks like in real life. This is in Hilo, Hawaii. Hilo is, I think Hilo is where the Hawaii International Airport is. I think that's where the airstrip is. But it's not only is it protecting against increased sediment load, it's also a barrier for storms. As you can imagine, if a storm surge hits that, it's gonna maybe not stop the storm surge from going over it, but it's gonna slow it down pretty significantly. So anything on the back end of that breakwater bay is gonna be a little more protected than just if you're right in front of the shoreline. So that really helps as well. Then we can have detached breakwaters, where they're not attached to the shoreline whatsoever. You just throw it out into the middle of the ocean, maybe a couple dozen meters off the shore. They're just made of the same stuff, riprap or concrete. Riprap is just those big ass boulders that they break apart and throw together. The parallel of the shoreline. So while we're still going to get some stuff on the outsides, we're minimizing that direct wave impact as a whole. So it'll eventually create these kind of shapes along the shoreline. So we're going to get a little bit of erosion in between them, but deposition on the back end of them directly. All right. Let me see. I think this is our last hard structure that we have. So this is probably one of the oldest ones that we think about. This is a seawall. So it's literally just a brick wall right in front of the dune. So older ones were made with just vertical stone. But what we came to realize is that as the wave crashes against the seawall, that crashing motion enables the wave to go over the wall and spill over. So the newer ones are, they're curved outward. So rather than the wave sloshing over, it sloshes against it and it gets pushed back towards the ocean. So that's how we've developed new ways of building seawalls that'll help prevent any overwash, because whenever you build a seawall, once it gets over, it's hard to get out. So you don't want to have any back flooding, because that'll be just as difficult. The problem with these is they're super, super expensive. For every meter, so from here to there, that's $10,000. And as you can imagine, the shoreline is really long. So $10,000 a meter adds up really, really quick. And that's including building costs, engineering, and construction. Like everything in, $10,000 per meter. What that doesn't include is maintenance. So if something happens to it, maybe someone was a little too excited with the jet ski, they crash into it, they get a big hole in it. That's going to make up your cost. Maybe you get some subsidence. What if we have another earthquake? We're on unconsolidated sediment. That seawall is going to shift. So they have a very limited lifetime, very expensive to build, very expensive to maintain. Not the best structure that we have. So that's a terrible picture, but that's what they look like curved. That helps to prevent anything from sloshing over. The newer ones, these are actually still pretty old. The newer ones have like a really sharp angle to it. It's almost like a trough. So it, like, all the energy is directed directly backwards. So they're pretty crazy. But taking into account price points and just energy required to engineer all these structures. The best thing that you can do is have the beach itself. Just having a natural beach is a great thing. Building on barrier islands has never really been a great idea. Even people, whenever they were colonizing most of North Carolina and Virginia, they didn't build on barrier islands just because you had all that overwash that could happen. So they built on the back end of the barrier islands, helped make you had more stable soil, more stable everything. So they're obviously really good preventing erosion, just because if you have a wide beach, you have a really big storage reservoir for sediment. You bring all that beach sand in and prevent stuff from encroaching inland. You can also get offshore sediment too, because the higher that we build that continental slope, that means we have more shallow waters. So we're going to decrease any of that wave action energy. So remember, all that energy comes from deeper waters. So if we can build up that sediment offshore, we can decrease that wave action, prevent erosion a lot from happening. Now, so because we know what we do about how effective natural beaches are, there are a lot of things that we can do. One thing that we can do is beach nourishment. I do not want to sway your opinion in any direction or the other, because my job is to give you knowledge, and what you do with that knowledge is up to you. But I will tell you that beach nourishment is the dumbest fucking thing in the entire world. It is the stupidest thing, the absolute stupidest thing that you can ever do. If you use it by itself, which a lot of beaches do. So obviously beach nourishment is just bringing in sand from somewhere else and dumping it on the beach. And then obviously you comb it out and do whatever. So you widen that beach surface. So you're basically creating a new source of supply of sediment, which sounds great, doesn't it? Well, it's not. Let me tell you why. So number one, you can't just get any old sand. Remember, sand is a grain size. It's just some type of broken rock down to a grain that you can still feel in your fingers, but it's still pretty small. But to have something be used as beach sand, it has to be pretty sand. It can't be any old sand. It has to come from a pretty rock, basically. So you get those nice white beaches along the beach shore that people like to look at. So that adds a cost, because that white sand is not found everywhere. It's very rare to find that white sand. It is only found in certain deposits. So you can either find a mine that has quartz, where you blast it, smash it down into sand-sized grains, then truck it hundreds and hundreds of miles to the coast, dump it there, and then a year later, that erosion is not going anywhere. It's still, those erosive forces, they're still there. They're gonna take it away. So eventually, so all you're doing is just dumping stuff, waiting for it to go away, and then saying, oh shit, we gotta get more. So that's what beach nourishment is. So form your own opinion on it, but my 2 cents is it's the dumbest fucking thing ever. I'm not even gonna watch this video because it's so fucking stupid. So yeah, so this is what beach nourishment looks like in Ocean City. So phase one, we have 1988, 1.7 cubic meters of sand. That is a huge amount of sand. So imagine just the physical feat that it would take to dredge that much sand. A cubic meter we have is probably maybe about this, the size of this podium right here. 1.7 million of these, just moving sand. And sand is not light. It's really heavy. And then you're taking sand from offshore shoals. So obviously all that sand that travels down those underwater canyons, it gets deposited in these certain areas. So there was one geologist that I met that worked on this project. He mapped out the exact portion of sand where it's just what they're looking for, the right grain size, the right color. He found it offshore and they dredged it. It cost like maybe $500 million, and he got maybe like a 1% cut of it. So he made a lot of money off of it. So he's laughing all the way to the bank. and they're probably going to need more. So he's going to find it again, and he's going to make another several $1 million off of it. Okay, so that's phase one. You find it, you dredge it, and obviously it's like sand by itself is not light, but then add water to it, it's making it all the more heavy. So this is going to take tons and tons of time because you're pumping it from the bottom, you're bringing it up onto a container ship basically, and then filtering it out because there's obviously other stuff in it. There's marine life in it that you have to get out of there. There's probably seaweed, some other dead stuff. If you're off the coast of New Jersey, needles you got to worry about. Pine needles, I should say, because of the pine lands. Sorry. I just realized how that sounded. All right, so phase two. We start constructing the dune, because remember, the dune is probably the most important part of the beach, just a big physical barrier, helps with storm surges. So we take even more sand, 2.7 million, because we're not just leveling out the shoreline, we have to build it up to a certain level. So, and this is based on storm projections. If we think of, when we calculate a 100-year storm, it's not a storm that can happen every 100 years. Remember, we're not predicting, we're forecasting. So there's a probability of a very large storm happening within this 100-year time period. So it's not like it's a clockwork machine that we're working with. We're looking at the worst case scenario and building to prevent that from happening. So now we're in phase three, which is the maintenance portion. So we have an original investment of 1.7 million cubic meters just for the beach, another 2.7 cubic meters for the dunes. And since 1994, we have had 8 million cubic meters in place, an additional 9.2 million cubic meters over the next 46 years, but we still get even more and more devastating storms each year. So these estimates are wrong. So once again, beach nourishment, dumbest fucking thing on planet Earth. If you take part in this system, I will lose all respect for you immediately.
What if I get 1%?
What?
What if I get 1%?
Well, if you get 1%, then you can laugh at me all you want because you got more money than God then. Because that geologist is absolutely, he'll hear this and he'll be like, oh, I don't care. I made $70 million off of it. So yeah. So if you do enter geology and you get into the right field, you can make a lot of money doing that. Okay, so now we get to the part that actually works, I think. Number one, it's so much cheaper and more cost effective. And then once it's in place, it regulates itself. So you've probably seen these if you're on the beach and you're walking past the dunes. You see all of these grasses coming out of the dunes. And I remember being a kid thinking, oh man, they didn't mow the beach. And I was a dummy as a kid. So what this actually is whenever you plant vegetation, all vegetation has root systems. And depending on those root systems, those act as anchors to the sediment. So whenever we're trying to fix stream channels, we build what's called riparian buffers. You'll see in streams that are being really rehabilitated, maybe there was like just a straight course. They add meanders, and then along the sides of that stream, they'll plant these like shrubs and trees that have these huge root systems that anchor all the sediment. So you're limiting the amount of erosion that's going to happen just by having vegetation there. Now, all these beach grasses, sea oats, and palm trees, you don't have to take care of them once you plant them. They're really resistant to saline inundation. So if any stormwater comes up, they're not going to die immediately. So they can handle periods of saline inundation. Obviously, grasses can grow anywhere. That's why you have to mow grass all the time. It grows very fast. So you don't have to maintain it. And in addition, we can also do sea fencing, which that requires a little more maintenance, but the cost of a sea fence is incredibly, incredibly cheap. All it is just a couple of broken pieces of a pallet and just some wiring. So really easy to maintain, really cheap to make, low upfront cost, low maintenance overall, so much better. And of course, as with everything, we're going to monitor it. So there may be some areas where it's a little weaker than others, where we're like, okay, gotta put more seagrass here. We gotta fix this sea fence, stuff like that. But because of that, we've built up a dune. It's more or less able to maintain itself. It's not going to cost us much to maintain it. Much better system for everyone. And of course, for whenever we're talking about this class, we're talking about hazards. If we have a lot of coastal erosion, that's linked to a bunch of other hazards that we've talked about or are going to talk about. So we've talked about tsunamis, earthquakes, and volcanic eruptions. Both of those can cause significant change to the shoreline. Obviously, tsunamis, if you have dunes in place, that's going to act as a helpful barrier. If you're living in a different environment where you have marshes, that's going to soak up a lot of that tsunami energy and tsunami water. So that's helpful. Earthquakes and volcanic eruptions, we can't really prevent those whatsoever. But they'll affect the shape of the shoreline as well. As we know, unconsolidated sediment behaves like a liquid when you shake it. So if we have stuff built on beaches and we have earthquakes like we did in Mineral, Virginia, it was not a huge earthquake by any magnitude, but because of the site conditions, we could have had a lot of sinking of buildings, a lot of foundational and structural damage just because of what it's built on. So we have to worry about that. And then obviously landslides, as we're eroding stuff from sea cliffs, you're destabilizing the base of a structure. And as you just much like somebody chopping down a tree, eventually all the stuff up top is going to fall over. So we have to worry about those if we're built on high cliff sides, like on the West Coast or up on the North Coast of Maine, built on cliff sides that get a lot of wave action. And then of course, on top of all of this, we have climate change. If the sea level is going to keep rising, we're going to have to keep building seawalls or keep building dunes higher and higher. So that's going to create a lot of problems. It's also going to increase the amount of storms that we have. Not only the amount, but the intensity of them. They may be stronger. For example, that trend that we saw with hurricanes at the beginning of the lecture yesterday, from 2017 to 2020, we had a greater number of tropical depressions. As we went through those 4 years, a greater number of those tropical depressions made it to storm status and then hurricane status. So that's a worrying trend. So if we have that on top of all of this, that's going to be a severe problem. Okay, and that's all I have for coastal hazards. That actually went pretty fast. Okay, so here's what we can do. We can either start the stuff on climate change, maybe finish tomorrow and have a little bit of time for on Thursday for a review session, or we can end today and start fresh tomorrow on climate change. So what do you guys think? We still have another 45 minutes until class is supposed to end. So that's up to you guys. Just a room full of no opinion, huh? Tomorrow? Okay, got one for tomorrow. I'm seeing some shaking heads. Is that a general consensus? Okay, all right, we'll start fresh tomorrow on climate change. And have a great day, everybody.